What is meant by the term the dual nature of electromagnetic radiation? So, what it means is that electromagnetic radiation behaves as both a wave and a particle. It shows characteristics of a wave and characteristics of a particle. To go deeper on that, the diffraction and interference of electromagnetic radiation shows that it behaves as a wave, and the photoelectric effect shows that it behaves as a particle. But the dual nature of electromagnetic radiation simply means that it behaves as both a wave and a particle. So that is 5.1. Let's go ahead and take a look at 5.2. So 5.2, a particle has 3.98 times 10 to the minus 13 joules of energy and has a wavelength of 5 times 10 to the minus 13 meters. The first question, 5.2.1, what is a photon? A photon is an energy packet. It's a quantum of light. That is the answer to 5.2.1. Let's go ahead and take a look at 5.2.2. What is the speed of a photon? We know that the speed of a photon, the speed of light, c, is equals to 3 times 10 to the power 8 meters per second. Nothing moves at a speed faster than that of light. And then 5.2.3, by means of a calculation, show that the above particle is a photon. How can we show that a particle is a photon? We can determine its speed and see if it is 3 times 10 to the power 8 meters per second. If it is 3 times 10 to the power 8 meters per second, then it is a photon. We have the energy of the particle, 3.98 times 10 to the minus 13 joules. We have the wavelength, and we're interested in the speed. Obviously, we have Planck's constant because it is a constant. So in order to determine the speed with these variables, we're going to say that the energy is equals to Planck's constant multiplied by the speed. Let's just put V because we cannot put C. We're not sure if it is a... well, the question is saying let's show if it is indeed a photon. But let's put V because at this point we're not sure whether it is a photon or not. Divided by... V is divided by wavelength because speed divided by wavelength is frequency. So let's go ahead and take a look. The energy, we have 3.98 times 10 to the minus 13 joules. Planck's constant, that is 6.63 times 10 to the minus 34. And then we're interested in V divided by the wavelength. The wavelength is 5 times 10 to the minus 13 meters. So let's go ahead and divide both sides by Planck's constant. So we're going to have 3.98 times 10 to the minus 13 divided by 6.63 times 10 to the minus 34, being equals to V divided by 5 times 10 to the minus 13. We divided both sides by Planck's constant. Obviously, on the right hand side, Planck's constant and what we are dividing it with will cancel out. So at this point, we can go ahead and cross multiply. If we do that, we're going to have 6.63 times 10 to the minus 34 multiplied by V, being equals to 3.98 times 10 to the minus 13 multiplied by 5 times 10 to the minus 13. We're going to divide both sides by the coefficient of V, which is Planck's constant. So V is equals to, well, let's just divide both sides at this point. So let me go ahead and divide by 6.63 times 10 to the minus 34. On the left hand side, they will cancel out, and then on the right hand side, 6.63 times 10 to the minus 34. Let me just put it in my calculator and not just assume that we're gonna get 3 times 10 to the power 8 meters per second. So I have 3.98 times 10 to the minus 13 multiplied by 5 times 10 to the minus 13 divided by 6.63 times 10 to the minus 34. I'm actually getting 2.97 times 10 to the power 8 meters per second. If we run it off to the nearest whole number, we would have 3 times 10 to the power 8 meters per second. But I think we can just leave it like that. That is 5.2.3. Let's go ahead and take a look at 5.3. So 5.3, will a photon of ultraviolet light have more energy or less energy than a photon of gamma rays? It will have less energy. It will have less energy, right? Because gamma rays has a higher frequency compared to ultraviolet light, and the higher the frequency, the higher the energy. So UV will always have less energy compared to gamma rays. Less energy, the saying, let's give a reason for our answer. We can say that gamma rays have a higher frequency compared to ultraviolet light. If you don't want to talk about frequency, you can say that gamma rays have a smaller wavelength compared to ultraviolet light. The smaller the wavelength, the higher the energy. That is 5.3. Let's go ahead and take a look at 5.4. So 5.4, name the type of electromagnetic radiation that is used to study animals at night. Well, leave a comment and tell me what the answer to 5.4 is. What do you think is the answer to 5.4?